Alrighty, so today we have Haskell, day 3. Haskell, day 3. So, there we are. Alright, so, now we're going to read about syntax in functions, which has some pattern matching stuff. Pattern matching is specifying patterns, which some data should perform. It should conform, and then checking to see if it does, and deconstructing the data according to those patterns. When defining functions, you can define separate bodies for different patterns. This leads to really neat code that's simple and readable. Yep. You can pattern match on any data type to make a really trivial function that checks if the number we supplied to it is a 7 or not. Then you have a classic example. If lucky matches 7, then that. Otherwise, you had a luck. All right. If it's not, it falls through. Could be used in a statement, but how about if you added more numbers, it would look like that. All right, cool. Note that if we move the last pattern to the top, it would always say not between 1 and 5, because it would catch all the numbers right. So if this was up here, that would always be called, and these would never be called. Define, remember factorial function? Okay, so now they're going to define it recursively, like so. Okay, cool. Recursion's important. I know how this works. We're all good. Pattern matching can fail, and if you call it, it'll throw an exception. I guess that's fine. That's not how Rust does it, but okay. Complains that we have non-exhaustive patterns. Should always include a catch-all pattern so that program doesn't crash if it gets unexpected input. They can also use it on tuples, right? You wanted to make a function that takes two vectors and adds them together. To add together two vectors, we add their x components and then their y components. Sure. Here's how we would have done it if we didn't know about pattern matching. Right. But this is nicer, I see. So you're kind of extracting it here and then using it like this. That's cool. That's very nice mathematical type way of writing it. FSD, so first and second, extract the components of pairs. What about triples? There are no provided functions that do that, but you can make your own. So like this. Cool. The underscore means the same thing as it does in list comprehensions. It means that we really don't care what that part is. So we just write an underscore. Which reminds me, you can also pattern match in list comprehensions. So you have a list of what looks like coordinates, and you're taking, and you're right here, you're pattern matching those. And if it fails, it'll move on. When would it fail? Oh, right. Yeah, I guess that's fair enough. Lists themselves can be used. Yeah, so x colon xs. So this is the classic. If you go and take some list, right? So let so I can do let j equals 1, 2, let x colon xs equals j. So now you have the first element, which kind of popped off. So this is kind of like a pop operation, except instead of actually modifying the old thing, it'll just return that element and the rest of the list. So this is like first head j and then tail j, right? Same thing basically. It's just a little nicer way to put it. And apparently that will fail to match on empty lists. So if I do j equals this, So yeah, it won't compute it until I actually try to use it. So that's interesting, but fair enough. Yeah, as it says, you can only match with lists of one or more. So empty lists won't work. It'll crash, apparently. Okay. If you want to bind the first three elements, you can use this. That's pretty cool as well. Now that we know how to pattern match against lists, let's make our own implementation of the head function, right? So here's your head function. Apparently, throws an error. Interesting. With that said, you can, it should say, yeah. And then if I do this, it should be that, that should be that. All right, cool. And I can also do, yeah, so that would kind of be like getting the last one. All right, so now you want to bind several variables. You have to surround them in parentheses. Yeah, so this apparently has to be in parentheses. Error function, don't use it very often, that makes sense. Calling head on an empty list just doesn't make sense. So I guess in cases like that, that's when you error. So really like panic and rest for, say, dividing by 0, right? Right, because it can't give you an integer back. It's just not possible. Anyway. Now you have tell. Okay. A little convoluted, but it makes sense. And what's it saying about this? Use list literal pattern. Oh, interesting. You can also do this. Oh yeah, in this case it makes sense. Oops. Right, but if I do this, and it'll say empty. Cool. Yeah, it says right here. That could be. So length of this is 0. Right, but then at the same time length of something else. So some x and then xs equals 1 plus the length of xs. Okay, let's use brackets here. Use folder, I don't care. All good. Yeah, so pretty much exactly like word for word what they wrote here. And you don't have to care about this even. Pretty neat. Factorial function as well. Right, you can also call length on, of course, a string, so I can go and say that in the 17. Well, what did I miss? Right, so this is just a quick recursion explanation. Let's implement sum of all the numbers. Okay, so you have sum of list of A returns an A, right? So sum, what's our base case here? Sum of an empty list is 0. Oops, wrong type. Add num A. Oh, right. There we go. Sum of some element and an empty list is that element plus the sum of the rest of the list. And let me bracket this. Oops. I know it'll tell me to use fold R. Do not care. Sum 1, 2, 3, 4, 5. But string should fail if I try to call it with a string, right? So that's pretty cool. Yeah, not bad. I can also do this, right? Pretty neat. For instance, all right, and then there's the at, which is keeping reference to the whole thing. So use xs at something, right? Right. Yeah, so this is the same as use the at. One more thing, you can't use plus plus in pattern matches, of course, because what would be in the first and second list? Right, right. It's not defined what the length of it is, because there are multiple ways you can get to the same list with. So you can do 1, 2, plus, plus, 3, 4, or you could do 1 plus, plus, 2, 3, 4, right? But when you're undoing that, how does it know which one you want? So you really have to use uh, the colon syntax, right? That's the only one where it's defined the length of, one of the patterns. Whereas patterns are a way of making sure that a value conforms to some form, and deconstructing it, guards are a way of testing whether some property of value is true or false. Sounds like an if statement, and it's very similar. Thing is that guards are a lot more readable, and they play really nicely with patterns. Okay. Wow, they're really clowning on everyone in the Haskell book. Okay. So that's interesting. But yeah, I see. So you have this kind of syntax of like is one of x if it is x equals 2, then 7. I don't know what I was thinking here. But what? Okay, interesting enough. Um, so it turns out white space is necessary, but whatever. Guards are indicated by pipes that follow a function's name and its parameters. A guard is basically a Boolean expression. If it's true, then that's used. If it's false, it moves on. Reminiscent of a big if-else tree in imperative languages, only it's far better, more readable. Sure, whatever. Otherwise, it is just true, and it catches everything. So this could also just be, yeah, but it's unreadable. So otherwise makes sense. Could have been called else. Uh, I'm dumb. Yeah, no, it could not have been because that's part of the if statement intact. Right. So let's implement our own max function. Okay, I see what this is going to do. So you're going to say max of A and B. Uh, if A is greater than B, then A, otherwise B. Oops. In fact, let me call this max. Yeah, makes just about sense. Not too bad. And yep, that's basically what they wrote. Guards can also be written inline, although I'd advise against it because it's less readable. You could do this though. There's nothing wrong with this, but does it want you to use? Well, obviously, but you can use that, and it would also work. Guards can also be written inline. Oh yeah, I read that. Let's implement our own compare by using guards. I'm not gonna write this one out. A my compare B means, okay, if A is greater than B, it's greater than. If it's equal, it's equal. Otherwise, less than. Cool, cool, makes sense. You can define them using backticks. Sure. So basically, you can define a function any way you would ever use it. So you could say like, I just made a function called that. uh, with that said, let me reload and do for, right? I could also define it like this, and then reload and use the same syntax. Or do. That's pretty funny that you can just define that and play around with it. Okay, so now let's talk about bindings. Uh, right. But writing this 3 times is bad. That's what they're saying. So when I take this, instead of writing this 3 times, I can just write BMI, BMI, and then, oops, where BMI equals this. And there you have it. Can you also do let in? Can I do that? Okay, so you cannot. You need where. That's reasonable enough. Put the keyword where after the guards. Then we define several names or functions. These names are visible across the guards and give us the advantage of not having to repeat ourselves. If we decide that we want to calculate BMI a bit differently, we only have to change it once. It also improves readability by giving names to things to make our programs faster. We can go a bit overboard and do, yeah, that's stupid. Where bindings aren't shared across function bodies, of course. We can also use where bindings to pattern match. Oh, so you're saying write it like this instead of this, and then have the pattern matching happen. Yeah, that also makes sense. Although again, don't just do this. And actually, there's a case for not doing it. This is not actually that bad. Let's make another fairly trivial function where we get a first and last name and give someone back their initials. Oh, okay. Uh, Initials of, which will take a string, by the way, and give you more or less another string. You could also write it as this, right? Eh, not that great. Initials of first and last equals. Wait, what does it do here? Oh, you wanna, I see. Yeah, I can't call it first name equals F plus where there we go. Uh that indentation fiasco is a bit interesting though. Alright, anyway, let's make another fairly trivial function where we get a first and last name. Okay, we did that. We could have done pattern matching in the parameters. Yeah, that's probably nicer, right? F, L, and just this. And then yeah, that makes sense. And better yet, you could probably just do F, L. That would probably be the same. So I guess it's style. This seems the best to me personally, but let's take a function that takes a list of weight height pairs and returns a list of BMIs. Yeah, I would use map for that personally, but that's basically what they're doing here by mapping it, right? It's cool. Where bindings can be nested. Okay. Very similar to where bindings are let bindings. Where bindings are a syntactic construct that let you bind to variables at the end of a function, and the whole function can see them. Let bindings let you bind to variables anywhere, and their expressions themselves are very local, so they don't span across cards. Just like any construct in Haskell, they can be used for pattern matching. Let's see them in action. Right, I've seen this before. You kind of just do let this in this. We could have also defined this with a where binding. Notice that the names are also aligned in a single column, so what's the difference? For now, it just seems that let puts the bindings first and where uses them after. That's what it seems to me too. Okay, but it turns out the difference is that let bindings are expressions, where bindings are just constructs. Yeah, if else you can put it anywhere. Uh, where let bindings you can. It turns out where bindings you can't. So huh, interesting enough. That seems eh, I'm not sure about that though. That seems kind of weird. Not square equals x times x in square 5, square 3, square 2. Cool. If we want to bind to several variables in line, obviously we can't align them at columns. That's why we can separate them. All right, with semicolons. Nice. Okay, that's what I was going to say. You don't have to put a semicolon after the last binding, but you can if you want. Like we said before, you can pattern match with let bindings. So this would also work. You can also put let bindings inside list comprehensions. Yeah, that seems useless. I'll just keep that. I see. So let bindings go away when you that's just a terminal thing, GHCI. Case expressions. Most languages have case syntax, and if you've ever programmed in them, you probably noticed about taking a variable and then executing specific blocks of code. Case expressions are expressions, all right. And then you can also do pattern matching. Okay. Interesting. Case of that. Okay. That's a way of pattern matching. Okay, this is cool. They're useful for pattern matching in the middle of an expression. And you could also do this. Cool. But then with that said, um, I'm probably done for now. All right, cool. So I'll get back to this another day.